All right, so mostly what I'm talking about is just kind of getting your data, manipulating it a little bit, just initial conditions with this same script that we've been looking at. Okay, so if you look over here, this is, in the first 20 lines of the code. Just make sure that you have all this stuff set appropriately, and you guys have already talked about that, so I think that you already know how to fill that out. The big thing that you're going to be changing when you, run and rerun this code over and over again is the initial conditions. So, like Yulun had said earlier, this is the initial state of the hole and the initial state for the electron. So what you're saying right here is, I'm photo-exciting this electron into this orbital, right, and it came from this one. That's what these IH and IEs are. And then you're letting the code figure out how they relax back down to the frontier orbitals. And so, yeah, you'll see that this is obviously not in the index of the orbitals, so the way that you sort of think about what these numbers are basically is, this number basically tells you how far into whichever band you actually are. So IH equals 1 is the HOMO, IE equals 1 is the LUMO, and so if you go to, like, say, HOMO minus 1, that would be IH equals 2, HOMO minus 2 would be IH equals 3, and so on and so on, and then vice versa for the IE and the electrons. So the way that, at least that I figure out how to, I guess, like, what numbers to use for these is you look at the OS strength file, and let's see, because the OS strength file is rated in descending order of oscillator strengths. So what that means is that these top handful of rows here are going to be the most probable photo excitations to happen if you were to just shine whatever incoherent light on it. And these are the energy differences too right here, by the way. So, like, if you're looking specifically for, like 3.5 eV photons, and, you just want to stick with excitations, I guess, that kind of match that criteria. So what you're going to do is you're going to take these and convert them into the IH and the IE. So I guess in order to do that, you need to know what your HOMO is, but that should be right there looking at you anyway. So you see that 450 is 4 orbitals into the valence band, right? Because you got 453, 452, 451, 450. So that means that IH would be 4 in this case. And likewise, this is 13 states above the LUMO, so it's going to be 13 plus 1, right? So you get 14 for your IE. So once you do that and you try to run your code and hopefully it doesn't crash on you and you actually get results, Yulun had already kind of talked about these. These are a very big one. But you'll also get these green figures, and I guess, do you guys know, like, how to interpret these? I mean, have you seen enough of them, I guess, or is it still kind of iffy? That's mostly what this slide is. And then I pasted the system that this was for right there, so you can kind of see. Okay, yeah.
I'm just selling copies of your masterpiece.
So what these figures are telling you is so you have, like, some instant in time, right? So you got, like, some vertical strip here. So in this case, this is the position versus time. So what that's telling you is that each position, right, in your system, which corresponds to the vertical spot right here, the other 2 dimensions are just integrated out. If you're seeing just this background green color, that means that the charge density is the same as it was in the ground state, so it might as well be the ground state at that position. So, like, say, initially right here in the titanium dioxide, there's really no change right after you've done your photo excitation. It's...
Yeah. Is it okay?
Yeah.
So, our audience is split on 2 parts.
Yeah.
In a sense. So one part is looking for optical signatures, like photoluminescence, and another part looking onto charge transfer, charge current density. So which of these parts your slide is primarily directed
This would be for absorption, not luminescence.
Charge transfer.
Yes,
So
charge
it's
transfer.
more for electronic rather than optical applications.
Correct.
So, on your opinion, who would appreciate this slide more, David or Kevin?
I can't remember what you guys are doing right now, so I don't know.
Ask them. It's very informal.
What are you guys looking into at the moment?
I'm studying PPTE nanowires.
Okay. Like, what about them, I guess? Like, are you looking at optical properties, or?
Which application?
Okay, so I guess for my nanowires,
Yep.
I'm specifically looking to see how durable they will be at like higher temperatures, so like semiconductors.
Okay.
But what is application of these materials? Which
Is it a lead in a diode or is it like solar cell?
either one? the third one. You know it. One word. So both you and Kurt, who was presenting after you in class, introduced why those materials are needed. I have a written record of you answering this question in the past. First letter C, T, T. Second is two words. And second part of the word is E.
Thermoelectric.
Yes. Is there charge transfer involved in thermoelectrics?
Yes.
So you are primarily client of this slide, this presentation, this part of presentation
Yes.
by one.
All right.
So this actually kind of shows you the charge transfer through time. Okay, yeah, so the background green color just means that it's the exact same right there as it was in the ground state. If the brighter the yellow gets, that means the more negative, the more negative the charge density is right here than it was back in the ground state. Basically, it means that there's an electron hanging out right here. Or multiple electrons, depending on what you're doing, I guess. And then, vice versa with the blue, the darker the blue, the more localized positive charge is right there. So that means that there's a hole present there.
So if it's the same color going this way, does that mean the charge transfer is constant?
That means that the charges are actually kind of more or less stationary throughout that time. Because time is moving this way. So if there's nothing changing right here, throughout this part of the trajectory right here, you kind of just have holes hanging out like on these cesium layers, and then you have electrons hanging out, in like the p orbitals just outside of it, is kind of what you can see from this right here. And then after you get to about this point, you can actually see how it's getting blue up in here now, right in the titanium dioxide. This is actually a charge transfer right here. So you've moved a hole over, but in this model, unfortunately, the electron follows suit pretty shortly after. So you get like an initial hole transfer over into the titanium dioxide, and then the electron follows suit shortly after, is what you can see, kind of from this blue, then yellow, and blue, I guess. Yeah, so this shows that you actually get like an excited perovskite, and then it just turns into an excited titanium dioxide nanocluster. So, yeah, at the end of the day, it doesn't result in a charge transfer, but you do get a really brief backwards one from the application that was intended for. Yes?
I'm just wondering one thing, like initially it's like spread over more space and it's very intense color that's indicating the higher intensity of positive or negative charge,
Yeah.
right? And after the transition it's become very light color, also it's localized on a small area.
So,
What's happening in the total populations of the positive and negative?
and again, like, I don't, it's kind of all blocked out right here, but like, this color right here, this is actually like the most intense electron localization right there. Like this darker kind of like reddish orange, this means that there's like a little bit of negativity there. Yeah. So it's kind of, you know, a weak shell and then more or less a core, but then it gets really tightly bound right up there.
Right? I do not know the answer. I'm just
No,
theorizing
it's
on
not
the
a
fly.
question, it's actually
So
I'm just
both negative and positive charge can be in the same spatial
That also
vicinity,
can happen.
but in decomposition through atomic orbitals, they could take like p yellow on left and right in the p orbitals on lead, and this bluish can be also p orbitals of bromine, but they can be oriented to px, py, pz in different orientation. And if we integrate it on the one-dimensional slice, it will look like a sandwich, like orange, blue, orange.
Is it because
Make sense?
That's how I interpreted it. Especially because of the cluster, it's not like plane, so it's all the orbital or the densities kind of stacked on top of each other
Yeah.
in this picture. Whereas the other ones are you have more contrast just because it's layered.
Oh yeah, I think that was actually the projector messing with me, because on this screen, it's definitely a lot like brighter right here than it is up here.
But if you summed the time step, you would get 0.
yeah,
Correct.
so you should.
Yes,
So it's
because this
just
is a neutral
showing-
system and we just plopped an electron in a hole.
It's
you know,
just showing how much it deviates from the ground state.
Correct. Yes.
So although
So this tells you where the extra charge is, more or less.
we're like migrated.
Yeah.
So like the early time is more perturbed than the later time. Because you have bigger differences.
What do you mean by more perturbed? I guess that's what I'm
The
confused
electron density is less like the ground state than it is at late time.
I guess it calculates
Yeah.
separately.
Right and wrong.
Kind of, yeah,
Yes and
I mean-
yes and no. Here the electron and hole densities are subtracted from each other, and even if there is an excited state without charge transfer, it is substantial deviation from ground state. If deviations happen in the same spatial region, this diagram may not reflect it adequately.
So is exciton is transferring to the die, not just a whole.
Yes. And should I name it as Dexter?
Yes, the Dexter energy
energy
transfer. So that's what those look like on the green figures. Whereas, so this was the isopropyl model, the hydroxyl model where you actually end up with a charge transfer. What you ended up with, you know, in this region was kind of blue down through here, and then yellow kind of scattered up through here. So you actually have charge separated between your species at that point. Okay. So, when I was trying to run this code for a long time, it would basically just take forever. I mean, it would take me hours to even get, you know, a couple of those pictures. So like if you notice it running really, really slowly, but it's not crashing, and, you know, say you just kind of stretch out your picture a little bit, like this green figure, if you just kind of bring out the corner a little bit and it has to reload and that takes, you know, way too long, what might be happening is that your figure or your graphics renderer is what's slowing you down. So in Linux, at least, you can change it like this. I was never able to find like an option in MATLAB, like a menu option. There is a way that you can change it once MATLAB has started, I believe. But if you, this would work on Mac, I would think. Windows with that command terminal, I'm not really sure if that would work. But within the MATLAB folder, this is the actual program right here. So if you open it with this tag on it, instead of using the default painter's renderer, it'll open it up with the OpenGL renderer, and this made things actually bearable for me. So if it's running super slow, try that. Okay, so once you have your green figures, yeah, just like for reference, I mean, I don't have it on here, I guess, but if you wanted to throw a color bar that kind of shows, you know, what's more or less intense, I guess, on either side of the spectrum, you can just do that with, you know, insert color bar and it'll just plop it right in there. And this right here is the code that is responsible for making this figure. And I can't remember, I feel like there was some kind of issue with, you know, putting in the angstrom symbol without having done this line of code down here. But if you know LaTeX commands, you can just straight up put it in and you just tell it that you want to interpret it through LaTeX commands. So this, you know, /AA turns into the angstrom symbol. So you can do things like that. But yeah, if you're going to be making a bunch of these and you know that you want something to be consistent throughout all of them, try to put it in this code here, because otherwise, if your computer is as slow as mine, it will take you forever to do anything. Okay, so there's really nothing. Okay, so whenever you do one of these figures, you're going to have different, you know, like maximum and minimum values, which determine the color here. And so what will end up happening is that you'll get, you know, like a bunch of these different figures, and they'll have like slightly different background colors and whatnot, and you know, they just kind of don't really match, and it makes it sort of harder to look at and interpret because there's already a lot going on there. You can keep them all consistent by going into this color map menu right here, and just setting the min and the max to the same values for all of your green figures. So basically what you have to do is just figure out, you know, what's the maximum and the minimum, or, you know, give yourself a little bit of cushion. And then as long as all of the data lies within that, you'll have the same kind of center point for each one, that background green color, and then everything will sort of be on the same color scale. That's, I think, all I got.
Okay, well, thank Landon. Any questions specifically, especially from Kevin and David? So if you have questions but I'm not sure to ask in public, development type, to Landon as an email.
Yeah, I spent a lot of time making those, so if you're having issues, let me know.